So, how exactly does the US Navy launch a 30-ton F-35 fighter jet from a dead stop to a staggering 150 miles per hour in just 2 seconds? Well, it's a feat of engineering that leaves absolutely zero room for error. Because on a carrier deck, even a 1% glitch leads to every pilot's worst nightmare, the cold cat. If the launch system fails to deliver that full, violent punch, the jet doesn't fly, it plunges. It slams into the churning ocean, sinking faster than the pilot can even react, turning a cutting-edge aircraft into a 30-ton steel coffin. For over 50 years, the Navy relied on massive, high-pressure steam pistons to hurl jets into the sky. But today, the rules of naval dominance are being rewritten. To stay ahead of the curve, the military has developed a technology that feels more like a railgun than a runway. This is EMALS, the Electromagnetic Aircraft Launch System. It replaces boiling steam with invisible magnetic waves, creating a launch process that is as surgical as it is powerful. Step 1 involves the pulse, where massive rotors spinning under the deck store incredible amounts of raw energy. Step 2 is the linear induction, where magnetic force takes over, pulling the jet forward with mind-bending acceleration. And Step 3 is the release, where the fighter jet is unleashed into the sky with pinpoint precision. But, as we're about to find out, moving from steam to magnets isn't just about speed. It's about surviving the most dangerous 2 seconds in all of aviation. The transition from the Sledgehammer of the past to the Scalpel of the future is arguably the most dangerous part of the entire mission. Otherwise, the crew and the ship might not make it back alive. So how exactly does this silent power work? To understand how we harness this invisible force, we have to go below the flight deck, into the heart of the ship, where the laws of physics are being pushed to their absolute limit. This is a multi-stage process of energy manipulation that makes the old steam systems look like ancient relics. Step 1 is what engineers call the pulse. Imagine the entire power grid of a small city being sucked dry in a fraction of a second. That is the sheer amount of electricity required for a single launch. But the ship's nuclear reactors can't just dump that much power into the rails all at once without blowing the entire system. Instead, they use 4 massive kinetic energy storage rotors, essentially giant flywheels. Each one of these rotors is a staggering piece of machinery, weighing several tons and spinning at thousands of revolutions per minute. As the ship's reactors feed them, these wheels store up kinetic energy, spinning faster and faster until they are practically screaming with tension. When the pilot gives the signal, the system squeezes that energy out, converting it into a massive concentrated burst of electricity. It is a violent controlled release, nabbing every available watt and compressing it into a single high-voltage heartbeat. But how do you turn a massive electrical pulse into physical motion without even touching the aircraft? That brings us to Step 2, the linear induction motor. Think of the traditional circular motors you find in a vacuum cleaner or a Tesla. Now, imagine taking that motor, cutting it open, and flattening it out along a 300-foot track. This is the rail that sits just beneath the deck. As the electricity from the flywheels hits these rails, it creates a sequence of powerful magnetic fields that move down the track in a specific pattern. It's not just a static pull, it's a moving wave of electromagnetic energy. It acts like an invisible high-speed tsunami racing across the flight deck. The aircraft's nose gear is attached to a shuttle that surfs on this magnetic wave. There are no pistons, no boiling water, and no physical contact between the driving force and the rails. It is pure, invisible energy, unleashing a level of torque that was once thought impossible. This leads us directly into Step 3, the launch. This is the moment where theory becomes reality, and it is absolutely mind-bending to witness. As the magnetic wave accelerates, it carries 30 tons of advanced military hardware with it. Within the first 100 feet, the F-35 is already hitting speeds that would make a supercar look like it's standing still. Inside the cockpit, the pilot is slammed back into their seat by multiple G-forces, their vision narrowing as the world outside becomes a blur of gray deck and blue ocean. The EMALS system is so precise that it can calculate the exact weight of the plane and adjust the magnetic push down to the millisecond. It's not just a raw explosion of power, it's a calculated, digital surge that ensures the plane hits its takeoff velocity with staggering accuracy. As the shuttle reaches the end of the track, the magnetic field abruptly shuts off, and the jet is hurled into the sky, tearing through the air as its own engines take over. But perhaps the most impressive part isn't the launch itself, but what happens immediately after. This is Step 4, the reset. In the old days, after a steam catapult fired, the crew had to wait. They had to wait for the pistons to retract, and more importantly, they had to wait for the boilers to build up enough steam pressure for the next bird in line. It was a slow, agonizing process that limited how many planes could get into the air during a crisis. With EMALS, that bottleneck is gone. Because the system is entirely electrical, the flywheels can begin their recovery phase the moment the shuttle stops. Within 30 to 45 seconds, the energy is napped back into the rotors. The magnetic coils are cooled, and the system is ready to slam another 30-ton jet into the atmosphere. It is a relentless high-speed cycle that allows a carrier to flood the sky with air power faster than any other ship in history. Watching this process, it feels like we've finally mastered the Shenglong of naval aviation, a system that is cleaner, faster, and infinitely more capable. We have moved away from the era of heavy pipes and scalding steam into an era of digital precision. On the surface, the Gerald R. Ford looks like any other carrier, but underneath that steel skin, it is a masterpiece of electromagnetic warfare. However, this shift from mechanical brawn to digital brains isn't just an upgrade, it introduces a whole new set of stakes. While EMALS is a technical marvel, it also highlights a massive paradox in how we design our most powerful weapons. Because, as we're about to see, the very thing that makes this system so perfect is also what makes it incredibly vulnerable. To understand why the Navy is betting everything on this invisible power, we have to look at the sledgehammer it replaced and the hidden cost of choosing a scalpel over a club. So, why exactly is the old way of doing things considered a death sentence for modern jets? To understand the transition from steam to magnets, we have to look at the hidden violence of the old way. For decades, the Navy relied on what engineers call the sledgehammer. This was the steam catapult. It was a massive, clunky, and incredibly powerful machine that used boiling high-pressure steam to jerk a 30-ton aircraft into the sky. But here's the problem. A sledgehammer doesn't have a volume knob. When the steam valves open, the pressure hits the aircraft's nose gear with a staggering, bone-jarring force. It's like being hit in the back of the head by a wrecking ball. This violent jerk creates massive amounts of metal fatigue, literally vanning and crushing the aircraft's airframe over time. Every single launch with a steam catapult was essentially a controlled collision that shaved thousands of hours off the life of a billion-dollar fighter jet. The Navy was effectively killing its own planes just to get them into the air. But why is the move to EMALS such a mind-bending shift? Think of it as moving from a sledgehammer to a surgical scalpel, while steam is an all-or-nothing system. EMALS is a masterpiece of digital precision. On a traditional carrier, you can't easily launch a lightweight drone and a heavy F-35 back-to-back.
The steam pressure is too blunt. It would literally tear a light drone into pieces, or fail to push a heavy jet fast enough.
But with EMALS, the computer controls the pulse down to the microjoule. It can dial the power back for a small, 200-pound drone, or unleash a mind-bending surge for a fully loaded fighter jet. It is a level of adjustability that was once thought impossible in naval warfare. It's like the difference between pushing a car with a bulldozer or guiding it with a precision laser. To give you an idea of the staggering power we're talking about, let's look at the scaling. The magnetic force unleashed during a single EMALS launch is equivalent to the horsepower of over 40 school buses, all hitting the gas at the exact same moment. That is a tremendous amount of weight and energy moving in a single invisible wave. And on the flip side, the old steam systems were even more terrifying in terms of raw pressure. The pipes carrying that boiling steam beneath the deck were pressurized to over 1,000 pounds per square inch. If one of those pipes were to rupture, the resulting explosion would be powerful enough to level a small skyscraper. Living on a steam carrier was quite literally like living on top of a giant, pressurized bomb that was constantly ticking. But as we know, what goes up must come down, and even the most advanced systems have a fatal flaw. The Scalpel of EMALS brings a whole new set of dangerous risks. During the testing phase of the USS Gerald R. Ford, engineers encountered a problem that nearly stalled the entire program. It wasn't a mechanical break, but something much more subtle: electromagnetic interference, or EMI. Just like the helium leak that nearly claimed the lives of the Artemis astronauts. A sudden surge or leak in the electromagnetic field can be catastrophic because the system is so heavily reliant on software and digital power conversion. A single glitch in the code can cause a power surge that fries the ship's sensitive radar systems, or worse, shuts down the catapult in the middle of a launch. Imagine being halfway down the track when the invisible wave suddenly vanishes. You aren't just losing a plane, you're losing a pilot to a ghost in the machine. So how does the Navy manage to keep this digital monster under control? They use a series of advanced power conditioning systems designed to isolate the launch energy from the rest of the ship. It is a delicate balance of physics and computer science that ensures the screaming energy of the catapult doesn't interfere with the whisper of the ship's communication antennas. It is a near rectilinear path of engineering, a highly elongated balance where the need for raw power and the need for digital silence have to perfectly cancel each other out. It is incredibly stable when it works, but it saves the entire mission from a total communications blackout. The success of the Gerald R. Ford depends entirely on this paradox. We have built the most complex, most expensive warship in human history, all centered around a system that uses nam-chom to do what boiling water used to do. It is a staggering leap in technology that allows for more missions, less maintenance, and a longer life for our aircraft. But it also means that the future of naval power is no longer just about steel and oil. It is about bits and bytes. We have moved the battle from the engine room to the server room. And while the risk of a cold cat is still a terrifying reality, the precision of the EMALS Scalpel has proven that the reward is worth the risk. The US Navy has once again found a way. TOW hurl 30 tons of steel into the sky with the grace of a surgeon, ensuring that their dominance on the high seas remains unchallenged. But how do we ensure that these pilots, after surviving the most violent 2 seconds of their lives, actually make it back to the deck in one piece? For that, we have to look at the other side of the flight deck, the controlled crash. One, as the F-35's wheels slam into the deck and the tailhook snags the arresting wire, the tension that's been hanging over the flight deck finally breaks. One, another successful recovery. Another pilot home safe. This isn't just a victory for the person in the cockpit. One, it's a triumph for the small army of technical experts living beneath the steel skin of the ship. One, these are the men and women who master the electromagnetic beast, monitoring every pulse of energy and every line of code to ensure the EMALS performs with staggering precision, one launch after launch. Their dedication is what turns a billion-dollar experiment into a reliable weapon of dominance. One, at the end of the day, whether we're using boiling water or invisible magnets, the goal remains the same. One, bringing our people back alive. We are a small team of 3 people dedicated to decoding the world's most complex engineering mysteries. One, and we believe that stories like these are best told through the lens of human creativity. One, that's why every frame of this video was built from scratch, using Papercraft, cardboard, and stylized animation to make the invisible forces of the military world visible. One, no shortcuts, just hours of manual labor to ensure you get the highest quality technical breakdown possible. One, we want to thank you for coming along on this journey into the heart of modern naval power. But now, one, the question is yours to answer. After seeing the raw, violent force of the steam-driven past and the surgical, digital precision of the electromagnetic future, which one do you trust more? Do you believe the old-school reliability of steam can ever truly be replaced? One, are magnets the only way forward for the 21st century? Drop a comment below and let's get the discussion started. One, if you enjoyed this analytic animation, make sure to hit that like button and subscribe for more deep dives into the machines that shape our world. Thanks for watching.